So, hello everybody. Today we'll be learning about computational fluid dynamics, that's CFD, in specific because that runs as a background in K2 Aerosim. So let's just directly get into CFD. So before we get into the computational part of fluid dynamics, let's first check how you can solve a problem, right? So okay, so our main topic is CFD. Um, okay, so if there's a problem given to us, suppose we have a problem that's given to us. Don't mind my handwriting. It's just bad. But yeah, I'll make sure I'll explain everything properly. But yeah, so imagine you have a problem. You have three ways to approach it, right? I'll do it like this. So number one is theoretical, your theoretical way. Second is your practical way, practical. So this includes experimental, and the third one is your numeric way, a numeric solution. So you have numeric solution, right? And another name for this would be computational, because nowadays everything is done through computers, so we write it as computational. Correct. So let's take a example. So for theoretical, if I want to know, let's say I take a pipe and I want to know the flow, about the flow. Suppose I want to know the pressure at this point. Then using the velocity and the head distance, I can calculate pressure values, correct, everywhere at each point. So this is using theoretical formulas and theories. So it's not necessary that you always come up with a value for the parameter. It can also be patterns or trends, trends in the sense that I sometimes may not know what the exact value of pressure might be. I can just tell that P is inversely proportional to velocity, and using this I can just give a guesstimate of the value of pressure, right? So theoretical answers are not, I mean, solutions are not all, I mean, they don't have to be very accurate. Out of all three, probably one of the most inaccurate one I can say is theoretical. I mean, I'm not saying that it cannot be accurate, but yeah, it's you can't completely rely on a theoretical solution, correct? Moving on to practical. So experimental results are always the go-to, in the sense they are used as validators in this. So you use this solution to validate answers from theoretical and numeric solutions. So this is done using experimentations and other stuff. So these are values that you approach in real life. So these cannot go wrong until you do something wrong in the experiment. So yeah, this is the practical solution. And then you have numeric solutions. So in numerical solutions, what you have is you have a set of mathematical and physical equations. So you have equations that you discretize, and then you solve each of the equations, solve equations, and get to a solution. Correct? So this is how the numeric solution goes. So you have an equation. Suppose for this same example, so let me draw it here. I have a pipe, so I have water in it. Now, if I want to find pressure along each, you first, so in numerical methods, you divide them into smaller components. We'll look in these in detail. Don't worry about that. And then you apply each of the equations, conservational equations, um, onto this, and then you discretize equations. That means you make equations simpler in form. So if you have like partial derivatives, you convert them into forms or equations such that they can be solved using linear equations or simpler equations in short. So and then you approach to a solution that converges. That is how you find pressure or velocity or any parameter that you find across each of them, right? So this is how stuff works in a so this is an overview of how you would solve a problem. So you have three ways, that is theoretical, practical, and numeric solution. So all these use the practical as validators, in the sense that any value you get from the numeric solution or the theoretical, you do always validate using the practical or experimental values, right? So yeah, so moving on. Okay, so let's move on to the next part. So coming next, so now we have understood how you can approach problems. So now we'll go specific into the computational part, and that is the topic of our whole video, that is CFD, or computational fluid dynamics, right? So how can I define CFD? Well, it's just simple. So if I have a problem related to fluid and I have to solve it numerically or computationally, that is how I would define computational fluid dynamics to be. So it's more like a branch of engineering that uses numerical methods to solve or simulate how fluid flows, right? So if I have a fluid, so as I discussed above, you have theoretical, practical, and numerical method. So if I use the numerical method to solve problems related to this fluid flow, or in order to simulate how the fluid would behave in a given constraint or in a given region with a specific boundary condition, then that is what I would call computational fluid dynamics, right? So now you have few steps, and these are just general steps. So number one being, you first make a physical model out of it, physical model of the problem, physical model. Then you go to mathematical model, and then you go to numerical solution. You use numerical methods, and then you finally converge into a solution, right? So again, let's take the pipe as an example. If I have a pipe and I have a flow within it, so the first physical model would be to model this flow. So making a pipe and having water or any fluid pass through it. Then you have mathematical models. Those are the equations that govern the flow within it. So in the physical model, you will also include the equations, that the physics equations like energy conservation, your momentum conservation, continuity equation, etc. So those are physical models that, or physical equation that you will be modeling. Then mathematical models are usually discretization and linear algebraic models. So you will be using them to discretize and make the equation simpler. Then you have numerical methods which solve these all these equations, and then you go to the and then you get a converging solution, um, which is then used to find out the result, right? So till now it was just straightforward. Let's move on. So now getting into methods of CFD. So you have three methods. I'll just write methods. So number one being FDM, that is finite difference method. Then you have your uh, FEM, that is your finite element method. So finite element method, and then you have FVM, that is the most commonly used um, method for CFD. So finite volume method, right? So these are the three methods that you will be using for numerical methods in general. So I'll just discuss each of them in brief. So number one being FDM. So what you do in finite difference method is that you divide structures into grids. So just to be in general, I'll just say that for each of these methods, you do have to divide them into smaller parts. So for FDM, it's called grids. This type, I'll just write it. So you call it grids. So now each grids suppose have some value, and you find the value of another using neighboring values. But to find that, you you use difference functions. So in order to find values of parameters, you use difference functions. Now, these difference functions, I can write them as, there are three common ones. So one would be, I can write as dfx by dx is equals to f of x plus del x minus f of x divided by delta x. Then you have the second one, that is fx minus fx minus delta x divided by delta x. And the third one, that is f of x plus delta x minus f of x minus delta x. I'm sorry, f of x minus delta x divided by 2 delta x. So now if you see, these are normal Newtonian differential equations that you would have um, seen in your class 11th or 12th chapters of functions. So here, when you have differentiability, in order to write it as a limit, you use these functions. So these are called difference functions. So this is called forward difference. Then you have, this is forward difference, this is backward difference, and this is your central difference. So each of them can be used in order to find values of each parameter. So in short, your FDM is used to find a general slope or a gradient within the grids in order to find values using the difference functions, right? So you have used, I mean, you are finding the slope using difference functions. So that in general is your FDM method. So again, these equations, the three equations, it depends on the situation of when you can use it. Um, so also the errors that give also are different by each of them. So here, since it's a 2 delta x, usually our error is in terms of, um, I would say, O of n square. That is, you have you're more accurate in calculating errors or residuals when you're using the central scheme, right? So yeah, that is about FDM. Now coming on to FDM. So sorry, not FDM, I mean FEM. So let's go down. Okay. So now let's go to FEM. So finite element method. So in this method, you divide objects or your region into nodes, right? So last time I had told it's grids for FDM. Here you divide it into nodes. Um, okay, I'll just denote them as triangles for now. Yeah. So okay, this is nodes. So I'll just take a body and I've suppose divided them into nodes. Okay, just assume these are nodes of suppose a body like this, right? So what FEM does is, so once the geometry is divided into smaller elements, that is here as you see, then you approximate the solutions or the values of the parameters that you want, like any value. Suppose if I say, what can I say? Or suppose deformation is a parameter I wanna find out or figure out, then I'll be using functions called shape functions. So these are dependent on the nodes, the shape of the nodes, right? So depending on the shape of the nodes, you approximate a shape function, and with that shape function, you find the value. Now, for example, if I had to find if there is 0 degrees Celsius and it's here 72 degrees Celsius, and I want to find temperature over here at this point. So first I'll divide it into nodes, and then for each nodes you use shape functions. And suppose the temperature is T1, T2, T3, and then at here this point it's T4. So I can write it as T4 is equals to N1 T1 plus N2 T2 plus T2 plus N3 T3. So what does this N represent? N is your shape functions. So use shape functions to approximate values, to approximate a whole value for your value that you have to find. That is your T4 at this point. So this is FEM in short. So FEM is mostly used in structural analysis. Structural analysis. So if you have your calcilix, calcili-x, and you have your abacus. So these softwares use by Dassault, by Dassault Systems. So these both softwares used FEM because they are more into structural analysis than CFD. So this is all about FEM. Now we'll check on FVM. That is the most important for us um, from the CFD point of view. So we'll jump on to CFD, FEM. So FEM is the most commonly used method for CFD. So FVM, that is finite volume method. So the V here stands for volume. So as the name says, so if you have a grid, suppose, I'm sorry, a pipe, you divide it into control volumes, right? So let's take this, right? So I'll just assume these points. So you have divided this whole region into control volumes. So control volumes. And another name for control volumes is cell. So I've divided them into multiple cells. And now what FEM does is it applies conservation laws. So you apply conservation laws into each of the cell boundary. Each cell boundary, right? And so when you apply each conservation laws into each uh, boundaries or each cell, so technically what you would be finding is your flux, right? So if I have, suppose I have, this is the grid. So I have a point here that is P, and I have a point here that is E. Okay. So just that I'll be using the term 5 for any parameter. So the term phi, okay, I'm sorry, not psi, phi. So yeah, the term phi will be used to denote all parameters. So okay, now I want to find the parameter, the flux across here, right? So what FEM does is instead of finding at individual points, what it does is it finds along this phase. So it finds phase value for phi, right? So how you would find these, the value of phi will be touched upon later. So what FEM does is you divide a region into smaller um, cells or control volumes where you enforce conservation laws. Now these conservation laws can be um, any, again, as you know, your mass balance, your energy balance, your Navier-Stokes momentum balance, etc., etc., and or continuity equation. And then you find the value of the parameter at the face, right? So I'll just now flux, if anyone doesn't know, it's your sigma in minus sigma out. So whatever is has come in minus whatever has gone out. So that has to be conserved, right? So that is the main idea of your FVM, and that is what we use in CFD, correct? So now we'll just jump into PDEs. Okay, now coming to PDEs, or partial differential equation. So partial differential equations. So this is important because how equations transform is something you have to know. That is something that happens in the backend, but I'll just give a general idea. So you have three types of PDEs. I mean, if you have a general equation, that is a d2 u by dou x square plus b d2 u by dx dy plus c d2 u by dy square plus d is equals to 0. So this is a general equation of a partial differential equation, let's assume. And so now you can divide into three. So one, you have elliptical, I guess this two else, but yeah, elliptical, you have parabolic, and you have hyperbolic. So these are just to define a problem or a partial differential equation into three forms. So because this will be useful in order to solve equations once you have categorized into one of them. So in elliptical, you have this condition that b square minus 4ac is less than 0. Again, 11th standard, 12th standard mathematics. Here b square minus 4ac is equals to 0, and here b square minus 4ac is greater than 0, right? And now you have again few constraints like d to u by dx square plus d to u by dou to y, sorry, dou y square equals to 0. Here you have dou to u by dx square plus d to u by dx dy plus d to u by dy square is equals to 0. And here you have d to u by dx dy equals to 0. So this is something that you don't have to remember. You can just directly get it from these constraints, or if you apply these constraints, you will directly get this. Um, so that's something that's easy. We'll just shift to, so yeah, this is just basics of your PDs. I mean, just categorization. And now why this categorization is important is it's just that now if it's a categorized as an elliptical PD, so here it's mostly likely that you do not involve time as a variable. Here it is time dependent, parabolic ones dependent, and here it can be anything, but an example if I could say for this would be wave equation. It's an hyperbolic parabolic equation, sorry, hyperbolic partial differential equation. But yeah, so now hope you get why this categorization was important, because now if you get any of this form, you can say it as it doesn't involve time as a variable. So when it doesn't involve time as a variable, further you will see that you can call it as a steady state flow, steady state, that is independent of time. As time dependent, it's transient flow, that is time dependent flow, right? So that's why partial, it was kind of important to know what type of partial differential equation you're solving. But yeah, okay, Now moving to the next part, again one general topic is errors. So you can encounter a lot of errors in any simulation that you do, because of course um, this is something that you're doing as computationally, so you are bound to have errors. Now these errors can be of three types. One is your round of error, and this is simple as the word says, it's due to memory limit. So sometimes, I don't know, example, your 5.04328296 might be rounded off to 0.043, and yeah, that the rest of the part causes is an error. And next type of error is your truncation error. So in truncation error, so this is for approximations that you use or discretization methods like Taylor series. So as I told, when you are using your f of x is equals to f of a plus f of f dash a x minus a, right? And then plus blah 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 plus, I would say, r of n. So when you do this, now suppose I am only taking this term, right? For discretization, I'm not taking the whole, because again this goes till infinity, you don't know, right? So I'm only taking this term. So now rest of these terms is a residual, and that causes an error. So this is your truncation error. And finally you have your modeling error. Now modeling error is based on the models that you choose, like you can choose laminar or you have turbulent models. So now the problem is that these errors arise if you choose the wrong model for the wrong condition, or the wrong boundary condition, or the wrong flow situation. So those errors are considered as modeling errors. So like for example, if you have flow of like um, wind around, I mean air around airfoil, and you use laminar flow, of course it's not going to be correct. You're going to have turbulent flow, right? So that is when you get modeling errors. So yeah, this is all about errors, and this is like more of the general um, topics that we covered. So now from the next topic, it would be conservation laws and solvers. So we'll just jump onto that next.